Welcome to Probability and Probability Distributions. Today, we are diving into the normal distribution, arguably the most important and fascinating concept in all of statistics. We will explore exactly what it is, why it appears everywhere in nature, from human heights to exam scores, and how we can use its mathematical properties to make powerful predictions about the real world. Let us get started. To begin our journey, imagine measuring the height of every adult in a crowded train station. Most people are around average height, with very few being extremely short or extremely tall. If you graph this data, you get a smooth bell-shaped curve. This is the normal distribution. It is a continuous probability distribution, meaning it handles exact values rather than just whole numbers. The curve is perfectly symmetric, acting as a mirror image on both sides. The center is defined by the mean, while the spread is controlled by the variance. Because it naturally organizes data so beautifully, it forms the foundation of modern statistics. Now that we understand the shape, let us look at the mathematics behind it. This complex-looking equation is the probability density function. It calculates the exact height of the bell curve at any given point x. The symbol mu represents the mean, which anchors the center of our bell. The symbol sigma is the standard deviation, which dictates how wide or narrow the bell is. If sigma increases, the curve flattens and spreads out. If sigma decreases, the curve becomes taller and tightly packed around the mean. The constants pi and e naturally emerge from the geometry of this curve.
Working directly with that complex formula every time is incredibly tedious. To solve this, statisticians created a simplified baseline called the standard normal distribution. We shift the entire curve so the mean sits exactly at 0, and we scale it so the standard deviation is exactly 1. This allows us to use pre-calculated tables instead of doing calculus. Furthermore, because the normal curve is perfectly symmetric, its skewness is exactly 0. Its excess kurtosis is also exactly 0, meaning the tails are neither too heavy nor too light. It is the ultimate perfectly balanced baseline.
This brings us to the z-score formula, which is how we translate any normal distribution into the standard one. Conceptually, it measures distance. The variable x is your specific data point. Mu is the average and sigma is the standard deviation. By subtracting the mean and dividing by the standard deviation, the resulting z value tells you exactly how many standard deviations your data point is away from the center. A positive z means you are above average, and a negative z means you are below average. This simple transformation lets us compare completely different data sets on the exact same scale. Let us see this formula in action with a concrete example. Suppose a university exam has scores that are normally distributed. We are given that the class average or mean is 75 marks and the standard deviation is 8 marks. A student needs to score above 91 marks to receive an A grade. We want to find the probability that a randomly selected student achieves this. To solve this, we cannot easily use the complex density function. Instead, we will convert the target score of 91 into a standard z-score to compare it against our known baseline. Continuing with our calculation, we start with our standardizing formula. We substitute our specific values. The target score x becomes 91, the mean mu becomes 75, and the standard deviation sigma becomes 8. Subtracting 75 from 91 gives us a numerator of 16. This tells us the student needs to score exactly 16 marks above the class average. Finally, we divide that raw distance of 16 by the standard deviation of 8. The result is exactly 2. This means a score of 91 is exactly 2 standard deviations above the mean, giving us a standardized measure of how exceptional this score is. With our z-score calculated, we can rephrase our original question.
The probability of a student scoring higher than 91 on the exam is mathematically identical to the probability of getting a Z score greater than 2. Using standard statistical tables, we look up the area to the right of a Z score of 2. The table gives us approximately 0.0228. Converting this to a percentage, there is a 2.28% chance that a randomly selected student will score above 91 marks. This makes perfect physical sense, as scoring 2 full standard deviations above average is quite rare.
Before we move on to combining variables, let us look at a powerful shortcut called the empirical rule, or the 68, 95, 99.7 rule. This rule gives us a quick, practical way to estimate how much data falls within certain distances from the mean without doing any heavy math. It states that approximately 68% of all data points will fall within one standard deviation of the mean. If we step out to 2 standard deviations, we capture about 95% of the data. Finally, an overwhelming 99.7% of the data falls within 3 standard deviations, encompassing almost everything. Here we can see exactly what the empirical rule looks like visually. The horizontal axis represents our data values, centered right at the mean, mu. Notice the vertical dashed lines stepping outwards by 1, 2, and 3 standard deviations, sigma. The central shaded region shows that 68% of the area lies within just one standard deviation. As we widen our net to 2 standard deviations, the bracket shows we capture 95% of the total area. By the time we reach 3 standard deviations, the 99.7% bracket covers almost the entire visible bell curve, showing just how rare extreme outliers truly are. Another incredibly useful feature of the normal distribution is the additive property of independent normals. This property states that if you take 2 or more independent variables that are normally distributed and add them together, their sum will also be a perfectly normal distribution. Independence is key here. The outcome of one must not affect the outcome of the other. This property is very special as it is not true for most other shapes of data. When you combine them, finding the new center is easy. The new mean is simply the sum of the individual means. Similarly, the new variance is the sum of the individual variances. Let us look at the mathematical formulas for this additive property. We define a new random variable y as the linear combination of 2 independent normal variables, x1 and x2, multiplied by scaling factors a and b. The new mean mu y is simply the scaled sum of the original means. Averages always scale linearly. However, for the new variance, sigma squared y, notice that the scaling factors a and b must be squared. This is because variance is fundamentally a squared measure of spread. Because the variables are independent, we can simply add these squared components together without any complicated extra terms. Let us apply this property to a real-world example. A grocery store sells apples and oranges. The weight of an apple is normally distributed with a mean of 150 grams and a variance of 400 grams squared. The weight of an orange is normally distributed with a mean of 200 grams and a variance of 225 grams squared. If you pick one apple and one orange at random, what is the exact distribution of their total combined weight? Since both weights are normally distributed and independent, we can define a new variable t for the total weight, simply adding the apple's weight to the orange's weight. According to the additive property, we first find the center of our new distribution. The mean of the total weight is found by adding the individual means together. We substitute 150 grams for the apple and 200 grams for the orange, giving us a new average combined weight of 350 grams. Next, we determine how spread out this combined weight will be. We calculate the new variance by adding the individual variances.
Because the weights are completely independent, we simply add the apple's variance of 400 to the orange's variance of 225. This gives a total combined variance of 625 grams squared.
We can now bring all of our calculations together into one formal statement. The total combined weight T follows a normal distribution, denoted by the capital letter N. This new distribution has a central mean of 350 grams and a variance of 625 grams squared. If we ever needed the standard deviation of this total weight, we would simply take the square root of 625, which gives us 25 grams. This tells us exactly what to expect when we put both fruits on the scale, proving how powerful the additive property is for independent normal variables. Now that we have used these formulas, let us understand why the normal distribution is so universally important. It comes down to a mathematical miracle called the central limit theorem. This theorem proves that if you take enough samples of almost anything, even if the original data is completely chaotic and not normal at all, the averages of those samples will always form a perfect normal distribution. Because of this incredible property, engineers use it to set safety limits, doctors use it for blood pressure ranges, and factories use it for quality control. It is the reliable engine behind modern science and machine learning. Let us review the key takeaways from our lesson. First, the normal distribution is a perfectly symmetric, bell-shaped curve that naturally describes how data clusters around an average, completely defined by its mean and variance. Second, the z-score is a powerful tool that standardizes any data point, allowing us to calculate probabilities and compare completely different things on the same scale. Finally, properties like the additive property and the central limit theorem allow us to make highly accurate predictions about complex real-world events. You now have a solid understanding of the ultimate foundational tool in probability and statistics.